This is my third video about the best methods for reducing carboxylic acids to primary alcohols. This presentation is about the use of borane and sodium borohydride as reducing agents for carboxylic acids. Because of its high selectivity for acids and its relatively low cost, borane is one of the best reagents available for reducing carboxylic acids if catalytic hydrogenation is not possible. Structurally complex acids with a number of additional functional groups will often only be reduced selectively by borane. Various mechanistic studies suggest that borane reduces carboxylic acids by intermediate formation of an acyloxyborane, which undergoes quick transformation to a borate of the primary alcohol. I could not find any detailed studies about how this acyloxyborane is transformed into the final product and have therefore sketched here 4 dimers of acyloxyboranes which could be possible intermediates of this hydride transfer. A monomolecular transformation of the acyloxyborane to the final borate would imply highly strained transition states, which I do not consider realistic when less strained paths are available. The most important advantages of borane as reducing agent for carboxylic acids are its high selectivity, the mild reaction conditions, and the simplicity of the reaction. Compared to the cost of hydrogenations, borane and anhydrous ethers are expensive, what restricts the strategy to more complex intermediates of drugs or agrochemicals. Moreover, an aqueous workup will usually be required to hydrolyze the borate ester, and stoichiometric amounts of inorganic waste will be generated. In this example, a carboxylic acid was reduced selectively in the presence of a ketone, and a very high yield of the desired alcohol was obtained. This example illustrates that acids can also be selectively reduced in the presence of alkyl iodides without reductive cleavage of the carbon-iodine bond. This example shows that as little as 1 equivalent of borane is enough to attain acceptable yields. Cleavage of the amide bond of the starting acid also took place to a small extent despite the low reaction temperature. This is an example of the reduction of a more complex acid containing a number of other functional groups that could undergo reduction. Nevertheless, with a slight excess of borane, a high yield of the required alcohol was obtained. Simultaneous reduction of the ethoxycarbonyl group only occurred to a small extent, and no dehalogenation or reduction of the olefin was observed. Instead of gaseous borane, acids can also be reduced with solid sodium borohydride. However, this reaction is not quite as smooth as the reaction with borane, because borane forms a rather unreactive complex with sodium carboxylates. If only 1 equivalent of sodium borohydride is added to a carboxylic acid, no reduction will occur at room temperature because the sodium carboxylate borane adduct is stable. Only upon heating to about 60 degrees for several hours, this salt is converted into a mixture of sodium carboxylate and acyloxyborane, the latter undergoing conversion to a borate ester of the primary alcohol. Thus, only 50% conversion of the acid can be achieved with 1 equivalent of sodium borohydride, and an excess of borohydride will be required to achieve a complete conversion. In the presence of methanol and an excess of borohydride, high yields of primary alcohols can be attained, as shown by the first 2 examples on this slide. Sodium carboxylates were, however, unreactive under these conditions. Borane can be generated from borohydride by treatment with boron trifluoride etherate or with other electrophiles, even in the presence of carboxylic acids. The least expensive version of the strategy would be the use of sulfuric acid, as shown here. A number of other electrophiles have also been used with success, though. The example on this slide also shows that boranes can form quite stable complexes with amines, what may cause problems with the monitoring and workup of such reactions. Cyanoborane also forms stable adducts with amines, and their hydrolysis may require treatment with strong aqueous bases. Unfortunately, many other functional groups may be reduced by borane, but as mentioned above, If an excess of borane is avoided, selective reduction of carboxyl groups is often possible. Here's a list with some other functional groups that may react with borane. If a target alcohol readily forms carbocations, a further potential side reaction is the exhaustive reduction to an alkane. An additional potential side reaction is the formation of aldehydes if sterically demanding alkyl boranes are used as reducing agent. With unsubstituted borane, this should however not occur. Boranes can also act as dehydrating reagents and catalyze the formation of amides from carboxylic acids and amines. Therefore, acids should ideally be reduced with borane in the absence of primary or secondary amines. Because borane is a Lewis acid, it can also catalyze a number of other reactions, for instance the addition of alcohols to certain nitriles. Again, such reactions can probably be suppressed by using only the required amount of borane. Here's a list with some additional examples. Occasionally, the reduction of a carboxylic acid with borane proceeds only slowly, and a number of catalysts have been found which can help in such instances. Acidic reaction conditions and catalysts seem to be particularly beneficial for this reaction.